Hello everyone, I'm Jayakodi from James Cook University, Australia. Today I'm going to talk about my research on laboratory modeling of stresses within minefields and loads on barricades. Here is the content of my presentation. Mining generates two things. One is valuable minerals, which are used in different industries. The other one is mine tailings, which are unwanted materials and should be disposed carefully without making any disturbance to the environment. Mine tailing management can be done either by constructing mine tailing dams or through mine backfilling as shown in the figures. Now let's see what is mine backfilling in a bit of detail. Mine backfilling is the process of filling underground voids with processed mine tailings. This technique is mainly used in artificially supported mines where high ground support conditions are required. There are different types of backfills currently in use. Out of them, hydraulic fill and paste fill are the commonly used fill types worldwide. Backfilling provides significant benefits over tailing dams. The main advantage of mine backfilling is to achieve local and regional ground support for the mining progression and thereby controlling the ground subsidence. Figure 1 shows a typical structure of an underground mine where you can see the mined out stopes have been backfilled and also an enlarged view of a backfilling stope is shown in figure 2. In an underground mine, there are several sublevels along the ore body called horizontal drives connected to the vertical stope, which allow access to mine machinery and other underground services. Prior to backfilling, these horizontal drives must be blocked at suitable locations with rigid retaining walls called barricades. So what if a barricade fails? Failure of a barricade can be catastrophic. There have been several mine accidents reported with casualties due to barricade failures in Australia and elsewhere. Some failures were contributed by the underestimation of horizontal stresses on the barricade. Therefore, constructing a safe and competent barricade is a critical engineering challenge. Having said that, my research objectives were to analyze the arching effect on vertical stress developments within backfill mine stope, to investigate lateral variation of vertical stresses within backfill stope, to determine the horizontal stresses on drive barricade, and also to compare the laboratory modeling results with analytical solutions. Moving on to the methodology, the physical properties of the fill material used in this study were determined and shown in Table 1. These properties were matched well with the hydraulic fill characteristics determined using 25 separate Australian hydraulic fills, as presented by Sivakugan et al. And Reddicliffe et al. Figure 4 shows a laboratory model stope setup, also called the arching apparatus. A square-shaped stope with a breadth of 150 mm and a height of 900 mm was used, and the wall condition was varied from rough to smooth to simulate underground mine wall roughness and grain silo, respectively. Since the stope walls are very rough after blasting, the interfacial friction angle can be taken as the friction angle of the fill, as the failure occurs on the fill-fill interface, but not along the fill-wall interface. Therefore, a similar condition was created using sandpapers attached to the stope walls, and acrylic surfaces were used as the smooth walls to represent the condition of a grain silo. When the stope is filled with the granular hydraulic fill, the fill load is shared by the balance at the bottom, and the load cell reflecting the load carried by the wall. Thereafter, the vertical normal stresses at the bottom of the stope and shear stresses at the walls at the end of each filling step were calculated. Figure 5 shows a barricade laboratory model called barricade apparatus, comprising 310 mm diameter vertical stope and several drive attachments of square and circular shape with dimensions of 100 mm and 150 mm. The granular fill in the model was subjected to surcharges ranging from 30 kPa to 900 kPa, and soil pressures were recorded at the stope center, stope edge, and on the barricade face using 3 earth pressure cells attached in the model. And also the barricade offset distance was set at 4 different positions for each drive size and shape to determine the stress function as the offset increases. Let's look at what is soil arching in brief. When a soil mass moves between stable and unyielding boundaries, the shear stresses generated along the contacted area tend to reduce the vertical normal stress within the soil mass, and that is known as the arching effect. As per the figure 8, the vertical normal stress at the bottom of the field stope is considerably less than the theoretical lower burden pressure at each field height, given the fact that certain fraction of the field load is carried by the wall as shear stresses, and thus soil arching is clearly evident in the simulated mine stope. Marston has developed an equation to determine the vertical normal stress within the backfill stope as given in equation 1. The lateral earth pressure coefficient K is a soil parameter and is a function of the friction angle of the fill. There are few arguments as to what should be used as K in backfill stope analysis. The widely accepted two are the active lateral earth pressure coefficient, Ka from Rankine, and the at-rest lateral earth pressure coefficient K0 from Jackie. Figure 9 shows that the Marston's equation with K equals K8, Ka largely overestimates the vertical stresses. However, K equals K0 and delta equals 5 give a reasonable approximation to the laboratory results. The mine stope walls are generally more competent, and hence the wall movement is not expected in backfill system. Therefore, the backfill can be considered more stable, suggesting that K0 is more suitable and accurate to use in the Marston's equation. Furthermore, laboratory results from both rough and smooth wall conditions confirm that the vertical stress is continuously increasing through to 6 meters. However, the analytical solution suggested an asymptotic value for the stress at a depth as low as 4B. From the barricade model test, the lateral variation of the vertical normal stress at the stope base across the stope width for all surcharges confirmed that the reduction of vertical stress towards the stope edge is attributed to the shear stress developed at the stope walls, reflecting the arching effect. In contrast, Marston's analytical equation does not account for the lateral variation of vertical stresses, and hence the stress values remain constant across the full stope width at any depth of the field. The plot in figure 11 shows a definite correlation between barricade pressure and offset. This relationship was apparent for all 4 offsets and confirmed that the reduction of horizontal stress acting on the barricade with increasing offset, encouraging miners to construct the barricade as far as possible from the drive entrance. However, the common industry practice is to keep the barricade offset equal to the drive height to reduce the drainage time of the field. Puganathan has expressed an analytical equation to determine the horizontal stress on the barricade surface as given in equation 2. Laboratory results were compared with the Puganathan's equation in a dimensionless analysis as shown in figure 12. The analytical solutions show an overestimation of barricade stresses at an offset approaching drive height for both active and at-rest earth pressure coefficients. However, the at-rest condition is more comparable with the experimental results, justifying the same behavior as in figure 9. Furthermore, Puganathan's solutions also verified that the trend of the barricade stress reduction with offset is nonlinear. Here are the key conclusions from the research. According to that, it was shown that the Marston's equation gives realistic predictions of vertical stress variation within a backfill vertical stroke, provided K equals K0 and delta equals 5. Laboratory results verify the reduction of vertical normal stresses laterally across the stope width, with the lowest recorded at the stope walls. And also the barricade model test confirmed that the horizontal normal stress within the drive and at the barricade decays with the increasing barricade offset, and the variation is nonlinear. These are some of the references, and thank you for listening.